Hello everyone, welcome to this last video about integration by substitution. And this last video is only there to teach you a shortcut. If you don't know the shortcut, you can do all these questions by regular use substitution. But if you know the shortcut, this will be a great tool to do these questions where you can apply the shortcut. And in some advanced technique of integration, many of the computations requires you to compute an integral where it's a simpler use substitution. And when you know the trick, it really simplifies the computation. So the goal is to look at integration by substitution where the substitution is going to be a linear function of the form mx plus b. And to see the idea of the trick, we're going to start with an example not using the trick. So here, let us compute the integral of e to the power of minus 3x plus 1 dx. So here, there's only one choice for the use substitution, is to use the exponent of the exponential function. So here we go. Let's use u to be equal to minus 3x plus 1. So this means that my integral is the same as the integral of eu times dx, and now the goal is to find a formula for dx. So if you compute the derivative of u with respect to x of minus 3x plus 1, we're just extracting the slope here, we're getting minus 3, and if you swap those two things, you get that du over minus 3. That's my formula for dx. So back to my formula. So this is, let's just put all these computation in a box just to make sure that we're not mixing up everything. So now if you replace in my integral dx by du over minus 3, what you're left with is this very nice basic integral, the integral of eu du. Yes, there's a over minus 3, but I'm just going to keep it there. So since the integral of eu du is eu again plus c, but I'm just keeping that minus 3, the last step is just to replace u back to its linear equation, minus 3x plus 1 divided by minus 3 plus c. So here, what is the remark here? If you look at your final answer, we know the integral of ex is ex. We know the integral of eu is eu plus a bunch of c's. But now here, we don't have just ex, but we have e to the power of a linear function. Because ex goes to ex, you can see that your final answer is again e to the power of minus 3x plus 1, but I'm dividing by minus 3. So in other words, if you know how to integrate e to the power of a linear function, if you know that the integral of ex is ex, e to the power of a linear function will be again e to the power of a linear function, but you just need to divide by the slope. And this idea is actually true all the time. If you have a substitution question that leads you to a basic formula, if the substitution is linear, just apply your formula, keep the interior as a linear function, and just divide by the slope quickly, and you're going to get your answer directly. So this can be summarized in the next theorem here. So if you have a linear function of the form mx plus b where m is not 0, suppose big F is a primitive for small f, then big F at mx plus b over m is a primitive for small f at mx plus b. So, and this is really better understood with this remark here. So what really the previous theorem is saying is that if you're integrating the function f of mx plus b and you know that the formula for small f is big F, well, just use that big F formula at that linear function, but divide by the slope, and of course, sign everything plus c, and you get your answer. So it makes the computation way more straightforward. Again, if you want the proof here, not super important, but just in case you care. Okay, so let's show that this is indeed the primitive. So we want to compute the derivative of big F at mx plus b over m. Remember, m is just a coefficient. So here I can take the coefficient outside. So it's 1 over m times the derivative of, so here I'm taking the 1 over m outside, times the derivative of big F at mx plus b. So we're computing the derivative of big F of something. So we have an interior. So this is a nice chain rule. So you're going to get 1 over m. This just stays for now, 1 over m. Big F will become big F prime, the interior untouched, times the inner derivative, so times the derivative of the inside, where the inside is mx plus b, and the derivative of a slope of a linear function is just a slope, so you get 1 over m. And now by assumption, I know that big F prime is small f, not touching the interior, and then times m. Oh yes, you can see that the m cancel each other, and you're just left with small f at mx plus b. So again here, if you have to integrate small f at a linear function, so if your u substitution is linear, apply your formula, your basic formula, use big F, don't change the inside, keep it as it is, just divide by the slope. And what I'm going to do is basically do a bunch of examples using that trick. So my next 3 examples, I'm going to use the shortcut to compute them. And these questions, they become so nice when you know the trick. But it's a very good exercise to also do these questions using the regular way, like choosing the U correctly, and then doing the method completely. And then if you use the trick versus the normal way, you will see that the trick is way faster. So for example, suppose I want to integrate 3 times e to the power of 5x plus 3. So here I see that my u substitution, the choice for u would be my exponent, which is 5x plus 3. So because I know the integral of EU is EU, so if I was using u equal to 5x plus 3, I know that this is a linear function and the slope is 5. So now I can finish this question by saying, okay, 3 stays 3, it's just a coefficient. Because ex goes to ex, e to the 5x will go to e to the 5x, sorry, plus 3. But then because I have a linear substitution, I just need to divide by the slope. That's it. That's all. So very short and sweet question. So if we do it again down there, so we have e to the power of minus 0.1x. So again, this is a u substitution where the substitution would be linear because I know ex goes to ex. If I have e to the power of something, it will go again to e to the power of that something. So I'm keeping the 2. E goes to e again. So I'm keeping the exponent, but then I just need to divide by the slope. And the slope here is minus 0.1. And you sign your work with the plus c. Dividing by 0.1 is like multiplying by 10. So this can be a bit more cute if you say it's minus 20 e times e to the power of minus 0.1x plus c. And then finally, for my last example, I have 5 over a linear function. I know that 1 over x is ln of absolute value of x, or 1 over u would be ln of absolute value of u, because my denominator is a linear function. So I'm going to use substitution, and I know that my answer is going to be directly, so keep the 5 as a coefficient, ln of the denominator, so 2x plus 1 minus 1, and I'm just dividing by the slope of that line. The slope of 2x minus 1 is 2, so just divide by 2 plus c. That's it, that's all. So you just get your integration. So since you know that 1 over u is ln u, since my u is 2x minus 1, it's linear, you can just write your ln of your line divided by the slope, and you're done. Remember, this trick only works if the u substitution is a linear function. Again, if you don't know the trick, and if you redo these questions, and I strongly suggest that you do it, if you redo these 3 questions by using the corresponding u substitution that I wrote, you will find exactly what I got. But once you know the trick, I think you're going to be enjoying that trick. Anyways, for this video, for this section, that's it. That's all. Bye-bye.